So let me begin with some, anyway, sorry, but I want to say that I'm in no particular rush in these lectures, no special end goal in mind. So please stop me as we go. It's much more important to get a few concrete, actual, real things than it is to go through it. This is not a talk. Okay, this is supposed to be a school. We will have an exercise session. I will think of some problems for the exercise session. We can also discuss any questions you have for the exercise session. But please stop and interrupt me. It's Blackboard talk, and it's meant to be something that fits in your head. If by the end of these lectures, you can go away and build one of these polytopes yourself and figure out what they're good for and plot it on Mathematica and get an understanding of what it's about, these lectures will be a spectacular success. If you can't come close to doing any of those things, it will be a miserable failure. Okay, so let's hope that it's closer to being a success than a failure. Okay, but just in order to begin, just setting the context, also because I think I'm the first physics lecture, let me talk about the first sort of connection between scattering amplitudes on the one hand and combinatorics geometry, positive geometry on the other. And maybe a very zeroth order thing to say. Oh, by the way, maybe just another show of hands. How many people here think of themselves roughly as combinatorialists? Okay, great. Okay, so about half of you. Well, let me just say right up front here, I bet most people who love combinatorics maybe when they're 15 years old or something like that. Maybe not, but anyway, pretty young. I'm taking a time scale. We're going 10 years back. I know you're all very young. It's not totally ridiculous. If you imagine 10 years ago or 5 years ago, you're a combinatorialist. What is the stuff that you're studying? Is it relevant for talking about what happens when you scatter protons at the Large Hadron Collider? It would seem completely fucking insane, right? It's not remotely obvious that these things should have anything to do with each other at all. Okay, so just get that out of the way. This is a crazy connection between mathematics and physics. It's not the kind of thing where you sort of more or less expect these things to be somehow related to each other. When you first hear about it, it's kind of insane that these ideas are related. It's insane that cluster algebras have anything to do with physics. And not esoteric physics, not the partition function for complicated theory X on complicated manifold Y. This is ordinary particle scattering, just things that happen in the real world when you look out the window all the time. And the fact that there is some way of conceptualizing this very basic physics that's related to very basic and sort of deep, simple, but deep structures in combinatorics and geometry is kind of remarkable. Okay, so that's the setting. But why should such a connection exist to begin with? Well, when we think about particle scattering, we imagine a situation where there are some particles that are sent in from infinity, and something happens, and maybe the same number, maybe more, maybe less particles come out. Okay, and that's what the actual experimentalist actually sees. The experimentalists, incidentally, when we talk about these things, we normally talk about particle scattering in the context of sort of experiments that happen at the Large Hadron Collider or collider physics experiments. But I stress that these are not egghead esoteric things. Again, this happens everywhere all the time. Everything we see in the world is a concatenation of these scattering processes taking place over and over and over again. There's a reason why people going back to the Feynman decided to focus on this question. It's both a very practical question for what physicists do, but it's also very closely related to the basic fundamental laws of nature, controlled as they are by both the principles of relativity and of quantum mechanics. Okay, so they're very basic processes. They happen all the time. They particularly happen in colliders where you need to know them in some detail in order to be able to compare theory and experiment. But what I want to stress is that, at the LHC, we're scattering protons. The protons are around 10 to the minus 14 centimeters big. But the distances that these particles are coming in and out of is about the sort of size of the ring of the LHC, is around 27 kilometers. And 27 kilometers is pretty much infinity compared to 10 to the minus 14 centimeters. Okay, so that is to say, the idea is that the particles come in from infinity, they bang into each other, and they go back out to infinity again. Okay? The experiment, the observations take place at infinity. And that's the sort of key point. But in order to come up our usual picture for what happens, our usual picture for how to compute these things, says that while the observations take place at infinity, we're supposed to take the sort of blob here and fill it in with a picture of particle trajectories moving in space-time and bang into each other in various ways. Okay? And more complicated things can happen here and so on. Okay, so while the observation takes place at infinity, our formalism for doing the computations in quantum field theory has this picture of a space-time on the inside, not at infinity, sort of bulk, the interior of the space-time. And we have this sort of intuitive picture of the particles coming in, bang into each other. The pictures are local. That's reflecting the fact that interactions are local in space and time. And you're supposed to add up all the possible ways to draw these histories in order to be compatible with the principles of quantum mechanics. That's sort of Feynman's picture of the path integral and the sum over all histories giving you quantum mechanics. Okay? So in other words, what's going on inside this blob in the textbooks is a picture of particle trajectories moving in space-time, reflecting the wave function evolving in Hilbert space. Okay, so that space-time and quantum mechanics are the stars of the show in this way of thinking about things. And both of those objects, both the interior of the space-time as well as the Hilbert space in which the wave function is in principle evolving, are auxiliary concepts that are not there in the actual observable. Right? The observable doesn't know anything about either the interior of the space-time or the Hilbert space. Now, why am I going on and on about this fact? Because there is a very famous fact about these computations, that apart from the very simplest processes, where like two things go in and two things go out, two things in, two things out, you put on a graduate quantum field theory problem set. And maybe the calculations are a page and use it to decide whether to take the grad student or not. Okay? But the moment you do 2 to 3 or 2 to 4, the calculations become ludicrously combinatorially complicated, ridiculously complicated. But people discovered around 30 years ago that despite that fact, the final answer turns out to be ridiculously simple. Okay? Sometimes the final answer collapses to a single line. But this business about how simple the answer is not the point by itself. It's just the sort of tip of the iceberg that says there's something wrong with this way of thinking. It's obviously not incorrect. It's so correct that it's the most spectacularly successful framework for physics we've had in our entire history as physicists. It's these pictures that let us make 12 decimal place accuracy predictions for things like the magnetic moment of the electron and so on. This picture is not wrong, but the picture is clearly missing something. You see, the picture would make you think that if 2 particles come in and 3 go out, 2 particles in and 4 go out, the answer is complicated because there's lots and lots of diagrams. There's nothing you can do about it. Just qualitatively, it will make you think the answer is complicated. Not every question in physics has a simple answer. Part of the chauvinism of fundamental physics is to declare as uninteresting and engineering those questions that have complicated answers and focus only on those questions that have simple answers. Okay? But physics has a wonderful way of rewarding morally good behavior. And the people who have to do these calculations simply in order to help experimentalists make contact between theory and experiment discovered that instead of 100 or 1,000 or 10,000 pages of algebra, the answer could be 1 term or 3 terms or some ridiculously simple things. Okay? So that simplicity is an indication that we're missing something. This picture is correct, but there must be another picture, some other way of arriving at the actual answer that does not involve these ideas of histories in the interior and does not involve the evolution of a wave function in quantum mechanics. Okay, so that's actually what we're looking for. What we want is kind of another question. So, we want another way of filling in the inside of this blob. You give me the kinematics of the scattering process. You give me the momenta and the energies of the particles. And I somehow have a machinery or picture or framework to give you the answer. Okay. Where does that picture live? What's the canvas? The canvas is nothing other than the kinematic space. So there's a what are these amplitudes are a function of the four momenta, the energies, and the momenta of the particles involved. Okay, so this is some four momentum, that's some energy and some spatial momentum, let's say. Okay. The external particles have some masses. The masses may or may not be zero, which are given by the energy squared minus k squared. So these guys are not independent of each other. They have to live on this sort of hyperboloid. This is sometimes called the on the mass shell hyperboloid. But apart from that constraint, this is the sort of data that labels the process. You'll notice that if I'm solving for e squared minus k squared equals m squared, if I imagine using that to solve for e, then there's two branches, right? I can say that e is plus or minus the square root of k squared plus m squared. And that plus or minus lets us do something nice. It lets us think that all the momenta, the four momenta, are incoming. And I can decide which particles are actually physically outgoing and which are incoming by the signs of the energies. So if the signs of the energies are positive, by convention, we say they're incoming. If the signs of the energies are negative, we say they're outgoing. This, by the way, is a very early thing in any quantum field theory course that you can think about amplitudes in this way. And this is already a very early hint that there must be a radically different way of thinking about things. The very fact that the amplitudes have this trivial analytic continuation that allows you to think about them in an all incoming way immediately removes a picture of some kind of unitary matrix that's mapping from the past to the future. Okay? The fact that all of these different processes are secretly the same analytic function is not at all obvious in the normal way of thinking about field theory, but it turns out to be true. Okay? Anyway, so we're going to be thinking about the amplitudes in this way. And what happens in the conventional picture, so just to be very concrete, let's say you have a process with 2 in and 3 out, or we think about it in this more uniform way with everything in, what happens is that in the course of this computation, so if this is the momentum of particle P1 and momentum P2, when we draw these diagrams, Feynman's diagrams, in here, by momentum conservation, we have a particle whose momentum is P1 plus P2. And it's sort of obvious that if P1 squared equals m squared and P2 squared equals m squared, that does not guarantee that P1 plus P2 squared equals m squared. Okay? So while these particles on the outside are real physical things that end up in someone's detector, these particles on the inside are not. We call these virtual particles. Virtual or sometimes off shell, off the mass shell. They don't satisfy P1 plus P2 squared is not equal to m squared necessarily. And well, that's a very practical sense in which the formalism for doing the calculations involves lots of things, unphysical things that are not actually there in the answer. Yes?
Sorry, you said that gives a plus or minus for EI tells you that you can write all the particles as incoming.
Yes.
Could you explain that?
Yes, so if you imagine all the particles are incoming, then what momentum conservation means is that the sum of all the pi is equal to 0. And the sum of over all the I of pi mu is equal to 0. Right? So in particular means the sum of all the energies are 0, and the sum of all the k vectors are 0. Okay? Now, this is impossible if all the energies are positive, obviously. Okay, so the way you would normally write energy conservation, let's say in high school, is that the sum of the energies in is equal to the sum of the energies out. Right? That's where we now imagine these energies are all positive numbers. Okay? So all we're saying is that if we allow ourselves to think about the energies as some being positive and some being negative, we can think about everything as being in. But if the in energies are negative, it's secretly out. Does that answer your question? Right. All right. Okay, so in this standard picture, the picture that we fill in the middle of the space involves all these virtual particles. Here I've phrased it in the momentum space. In position space, it's exactly the same thing. It's pictures where particles go finite distances from here to there, right? Things go finite distances. That's not that's something compatible with the uncertainty principle, whether it's there or not. How it's particles that travel infinite distances out to where the detectors are at infinity that are the physical particles. So the usual picture is filled with an enormous amount of unphysical baggage in order to get the right answer. And what is that unphysical baggage there for? It's there to guarantee that the answer is somehow respects locality in space-time and some agreement with the principles of quantum mechanics that tells you that you should be able to think about these amplitudes as an operator between in and out states. So there should be some operator. We sometimes call it the scattering matrix. That and these overlaps between, so there's a unitary operator, and the overlap between the S on this in state and the out state is what we call these amplitudes. Well, the fact that this operator is supposed to be unitary, S dagger S equals 1 puts restrictions on what this function of the momenta look like. So we have functions that depend on momenta that are on shell. The usual way of doing the computation puts all sorts of off-shell junk in the middle of the calculation, whose entire purpose in life is there to make it clear that the physics is compatible with local interactions in space-time and unitary evolution in Hilbert space. So that's what this purpose of life of the standard formalism is. And it does so at the expense of making the answer look like it'll be 1,000 pages of algebra when it's one term. Okay, so that's fine, but that invites you to think maybe there's another machine for doing the calculation. Maybe there's another picture, another set of ideas that will directly get you to those final answers without introducing these auxiliary ideas. Okay, so that's been the sort of moving that's been the sort of central engine that's driven these developments over the past 10 or 15 years. So where should this object live? So, so we want something else that goes in here. So we don't want to imagine that there's trajectories in space-time and evolution in Hilbert space. We want to find another object, and it should live directly in the kinematic space. So we want to have a picture like this. But we want to have something else. We're looking for a different question. We're looking for a different question to which the amplitudes are the answer. And where should this question live? Well, what is our canvas? Our canvas is n momenta for the particles, right? That's it. All we have is momenta P1, P2, P3 up to Pn. Now, when you say it like that, it now seems like hopeless. Because what the heck could you do in the space of n vectors, right? That's our space. That's the space that we have to find a question in the space of n vectors to do something with. Notice this space is not like this normal kind of space that physicists love to play in. It's not a space that has a metric. It's not no notion of distance, no metric, no time, no evolution. This is the most austere, stupid space imaginable. N vectors. What could you possibly do in the space of n vectors? Right? And this is the reason. If anything like this is going to happen, it's therefore inevitable that the ideas, because there's nothing left, the ideas have to be essentially simple geometric, combinatorial geometric ideas. And that is indeed what we've found in the past 10 or 15 years, that there are in this ridiculously austere space of n momenta, thought about in various ways, there's just enough mathematical structure that you can begin and find amazing things coming out. Now, in your previous lecture, you've probably seen the earliest indication of this. Purely mathematically, here's another space where, at least you're a physicist, if you're me, you would think nothing interesting is going on in this space. Well, almost exactly the same space I told you, the space of n column vectors in a k by n matrix. What the heck would you do in the space of n column vectors? Okay, it's the Grassmannian, big whoop, right? It's just the configuration of n points, all right? Now, What is the tiny bit of extra structure that was added to this world to make it go in the previous lecture? Can anyone tell me?
Positivity.
Oh, but slightly before positivity. You say that all the minors are positive in the positive Rachmaninoff, right? Why is that a sensible thing to say? Guys, you guys suck. Actually, I don't know. You may or may not suck. Just you're very good at that. It's the ordering. That's a key thing, is that the endpoints are not given to you randomly, they're given you in an ordering, 1, 2, 3, right? Which means that if you imagine drawing them, let's say for k equals 3, you imagine drawing them projectively, right? So you take these 3 vectors and you imagine that they're points in P2. If you just give me random points in P2, I don't know what the hell to do with them. But if you tell me that they're labeled 1, 2, 3, 4, 5, 6, 7, then I can ask for something. I can ask for this polygon to be convex. And that's what the positive Rachmaninoff is. Okay, so that's a very simple example that once you've decided on an ordering, notions of positivity become available to you that are not available, obviously, otherwise.
Yes.
Yes.
Can you say a few minutes about the columns of the cosmologics? We really just looked at the row span as the point, not looking at.
Yeah, well, so they're just there are 2 equivalent ways. In fact, if you just think about k-planes and n dimensions and nothing else, you really don't even have a decent notion of column, right? You just have a bunch of row vectors, right? And you're supposed to take the span of these k row vectors in order to define a k-plane. So when we talk about the positive Rachmaninoff, implicit in the entire thing is that there's also a basis. There's also an interesting basis, and that I can equivalently think about it as a configuration of n column vectors. Okay? Now, in both cases, I'm supposed to think about this data up to GLK, and that GLK tells me if I think of it as endpoints, I should think about them as endpoints in PK minus 1. Okay, so since I can think of it up to GLK transformations, it's really n. At least if the columns are generic, I can think about them as endpoints in projective space. Okay, but it's still crucial to have a notion of ordering in order to be able to say something sensible about the minors, right? Because if I say the minor 135 is positive, it had better be that it's written in the order 1 less than 3 less than 5. Otherwise, talking about the signs does not make any sense. So I'm just giving this example since you just saw it, just to give you, because it's also purely mathematical, forget about all this physical motivation. It's also kind of a shock mathematically that you take such a ridiculously tiny space, ridiculously austere space of configurations of points, you add a notion of ordering, and all of a sudden, this incredible structure comes out of it. Okay? If you're just trying to understand general configurations of points, endpoints in projective space, this is a famously impossible problem. This is essentially the problem of stratifying matroids. No good solution, right? The ridiculous thing that you put this tiny bit of extra structure of an ordering, and all of a sudden there is a stratification that is given by positivity and the positive Rachmaninoff. Okay, so that's one theme that's going to that recurs in this story so far. We hope to be able to move away from this eventually, but we have a notion of ordering in this kinematic space. So let's come back to the question we're asking. We have this is our space. It's a space of n momenta. And fundamentally, it's a space of n momenta. Maybe n d-dimensional momenta. For imagining in general space-time dimensions, we might want to restrict it to e equals 4 as a special case. But anyway, that is our space. So that's one way of thinking about the kinematic space. And so you want to find a question to ask in the space of n momenta, whose answer is going to have all the richness and complexity of the scattering amplitudes in it, and in particular have all the analytic properties the scattering amplitudes have to have in order to be compatible with local evolution and in space-time and unitarity. Okay, so this question should live. This is our canvas. Our canvas is the kinematic space. Our canvas is the kinematic space. So we have to find a question in the space of n momenta that gives us an answer, which is scattering amplitude. Now, it turns out in detail, there's a few ways of thinking about this kinematic space. This is the most obvious one. And all you give if you had momenta, if you have particles that have no spin, the only data that they have is their momentum. In general, they can also have a spin. So it can also be a spin for these particles, an extra discrete index. Okay, so that's the real space. And so somehow in this space you want to that's our canvas. There's another way of thinking about the data, which is especially useful when the particles don't have any spin, which is that because of Lorentz invariance, the actual amplitudes only are functions of not the momenta individually, but dot products of pairs of momenta. Okay? So this is our second kinematic space. Our second kinematic space is fundamentally parametrized by the pi dot pj. Okay? And again, we can ask the question, is there a question in this kinematic space, the space of all pi dot pj, whose answer gives us scattering amplitudes? Okay? That's what we're after. All right. So the interesting thing, as I've said a few times now of the past 10 or 15 years, is that there are now positive answers to these questions. And there's sort of two settings in which this has occurred. The first one is actually closer here. In many ways, so this is the story of the amplituhedron, or gluon scattering amplitudes. And in Maxwell supersymmetric theories. So I think Mark is going to say something about these things. I'll just say very briefly, well, if you're a mathematician, you don't care. Probably either way. If you're a physicist, you're supposed to react to seeing n equals 4 super 8 mils with this big blah. Oh my God, what you're doing is just for this very simple, dumb toy. Supersymmetric theory has nothing to do with the real world. Why would I care about any of this? This is a toy model, but it's the toy model of all the toy models that we've studied in fundamental physics in the last 40 years that's maximally closest to the real world. Because the leading order of approximation is identical to the good old-fashioned gluons that live inside the protons that we scatter at the LHC. Okay, so it's a toy model, but it's not like in 2 dimensions for something we don't give a rat's ass about. Okay, in some approximation, it's something we actually directly care about. Okay, now more recently, and in many ways, this is a much richer and deeper and more interesting story than what has come afterwards. Okay? It's, I think, more novel and ultimately, I think, deeper and more interesting. But nonetheless, over the past sort of 5 or 6 years, and more of the past year or two, we've seen structures like this that live in this kinematic space for theories of to begin with, theories of scalars, but they generalize in interesting ways to more interesting theories as well, including, again, non-supersymmetric gluons. So this is the story of the icosahedron that lives in this kinematic space, in the space of the pi dot pj's, appropriately thought about. And it generalizes in an interesting way to all surfaces that's related to higher loop orders in the quantum field theory. But just so you have a rough roadmap, these are the sort of 2 kinds of structures that have been seen, and there's a lot of structural similarity between them. The main difference is the nature of the kinematic space. Here, the kinematic space is more directly 1 vector per particle. We don't actually end up using directly the momenta. There's something called twisters or momentum twisters that end up being more useful, but it's a detail. It's really 1 4-vector per particle. Okay, that's the kinematic space. Here, the kinematic space is in this interesting pairs dot product space. And much of at least of my own work over the past 5 years has lived in this space. And the connection and the generalization to cosmology is much closer to this space as well. Okay, so now what I'm going to do in my remaining time is tell you about this kinematic space and what the kinds of questions are and what the relationship is between these objects that we've seen in amplitudes and in cosmology. Okay, so this, again, this first lecture is really just to set the stage, and then we'll get down to brass tacks after we get back from the lecture. Any questions so far? I haven't really said much, so if there's questions, they'll probably not be too content. But, nonetheless. Okay, so let's understand our kinematic space canvas. And to begin with, remember, I'm going to just imagine that we have scalar particles, so there's no spin. So all I have is a bunch of momenta, P1, P2, up to Pn. The only thing I know about them is, so let's say that all the pi squareds are 0. They don't have to be 0. The particles don't have to be massless. I'm just going to put them to 0 so I don't have to talk about the mass. So you can trivially put the masses back into this whole story. Okay? In fact, let me not even say what they are, because they won't matter. They are whatever they want on the outside. But what I do know about these things is that they satisfy momentum conservation. Sum of pi mu is equal to 0. Okay. All right. Now you're going to be surprised, I hope, to see how much of the story comes out of momentum conservation, right? And if you're again, if you're a mathematician who has not taken a quantum field theory course, maybe you don't care about any of this. But if you're a field theorist, momentum conservation is the dumbest, most trivial part of the story. Every expression has a delta function for momentum conservation. It's so boring you forget about it. You don't even write it down in the formulas in the end. And this should not surprise you that if you're looking for a dual way of thinking about something, a second way of thinking about something, the things that are trivial in the standard way should play a more starring role in the new way, right? That's sort of obvious. And so thinking about momentum conservation turns out to be a very big deal in this entire story, okay? In different ways. There's in the story of relating amplitudes of the positive Grassmannian, thinking about momentum conservation plays one kind of starring role. Here it plays a much simpler sort of starring role, but it's nonetheless a very, very important role. So let's talk about it. Okay, so I'm going to represent this fact that I have a bunch of vectors that add up to 0 just by drawing the vectors. Okay, so I'm going to draw the vector P1, and then P2, P3, P4, P5, P6, Pn. And momentum conservation tells me that these form a closed polygon. So that is a cool thing. Now, can someone tell me, I made a choice here. What is the choice in drawing this polygon?
Make it convex shape.
That's not, I did, sorry, I shouldn't have done that. I could have drawn it less cut. By the way, it's even higher dimensional in general, right? So the convexity was kind of an accident. There was, but you're correct. My bad. Yes. That's another one. It's getting closer. No, the turning point doesn't much matter. Yes.
Uniform length.
Also, I'm just terrible. All right. I've learned. Thank you. No, it's also uniform length, more or less. But no, I ordered them, right? I said draw P1, then P2, then P3. That's it. Just give me the n vectors. Who told me to put them this way? So I need an ordering to be able to do this. Remember, talk like in your previous lecture, right? We need an ordering. We'll come back to what this ordering means in physics in a moment. And we need an ordering. Okay. But having defined this ordering, then what I've done is write each momentum like pi mu. I can really think about some points, like this is a point x1 mu, x2 mu, x3 mu. These are funny points in this space where the units of x are momenta. But anyway, I've written pi mu is xi plus 1 mu minus xi mu, and this trivializes momentum conservation. Okay, so just keep this in mind. So really, our data is this polygon, right? Now, but remember, everything is Lorentz invariant, right? So if someone just hands you this polygon, what is the Lorentz invariant information in this polygon? I mean, what's the first thing you would think of if you're a kid? You have a bunch of points. What's Lorentz invariant? Distances, right? So what's the data associated with this polygon? So all the distances. Let me take the distances between pairs of points. Okay? So I'm going to define an xij to be this little xi mu minus little xj mu squared. Right? So for example, if this was my polygon, then I could define x13 to be little x3 minus little x1 squared. But remember, this is P1 and this is P2. So x13 in terms of the momentum is also P1 plus P2 squared. x13 is also P1 plus P2 squared. Is that clear? And so in general, the xij are pi plus 1 plus dot dot pj minus 1 squared. Okay? So just taking the kinematic space gives you this polygon, and the natural kinematic object are these xij. Now, it's a very nice fact that of just counting, we're just going to count now in a moment, that in fact these xij's are a basis of all the possible dot products. So they fully specify all the possible dot products that you could actually have, right? So if we forget about this picture for a second and come back to think about the most naive kinematic spaces being in terms of the dot products, then maybe we could define these objects pi dot pj. Sometimes physicists call these guys maybe with a factor of 2. Sometimes these are called Sij. They're called Mandelstam invariants, but anyway, they're just Sij. Now, how many of these Sij's are there if I have n particles? How many independent ones are there? Well, I have n choose 2, except is that it? Yes.
-1.
A little bit more than -1. You see, these guys have a constraint. The sum of all the pi is equal to 0. So if I dot this into pj, dot into all of this, that's still equal to 0. So that tells me that the sum over j of Sij is equal to 0. Sum over j not equal to I of Sij is equal to 0. Okay? This is a very familiar thing you deal with all the time in physics. The spaces are always constrained in one interesting way or another, right? So, so you have to figure out how to deal with that. Should you think about it in terms of, in a more symmetrical way, in terms of what extra variables which satisfy some constraints? Should you try to solve the constraints explicitly and parameterize them in such a way that the constraints are gone so that you can just give free data, right? We always have this tension in physics. It's never obvious exactly how to deal with it, but a good rule of thumb is if it's possible to trivialize the constraints, do it, okay? So in this case, of course, how can I trivialize these constraints? I could just choose, let's say that I use this equation to solve for Pn as minus P1 minus P2 minus dot dot minus Pn minus 1. And that means that my invariants are this Sij where j is not equal to n. That's perfectly fine, but that's also horribly ugly because it breaks the obvious sort of cyclic symmetry that this entire problem has. I haven't told you the physics origin of that cyclic symmetry, but just the picture obviously has a cyclic symmetry. And so we're obviously doing some violence to that. Okay? All right. So that's one way of thinking about the kinematics is the Sij on the support of this constraint. So how many independent variables do we have there? It's n choose 2 minus n, right? Because there's one of these equations for every I. So this is the actual number of equations, nn minus 3 over 2. But notice this is exactly the same as the number of chords in this polygon. Exactly n choose 2 minus n, right? Does every pair minus the adjacent ones. Why don't I have the adjacent ones? Because the adjacent ones are just the p squareds that are not varied. The p squareds are locked to 0 or the math squareds or whatever they are. So that is very cool, that these xij's are both the geometrically natural things in this picture. They're also a basis for all the possible invariants. And since we have exercise sessions, I'll give you an exercise. So this is supposed to be a basis, so this is just some trivial linear arrangements. So I should be able to calculate what is this 2pi.pj in terms of the x's. Okay, and the formula ends up being the following, that negative 2pi.pj is equal to xij plus xi plus 1j plus 1 minus xij plus 1 minus xi plus 1j. Okay, so this tells you how to go back and forth between the obvious elements of the basis and these sort of cooler ones that are associated with the lengths in the polygon. Okay, it's a very simple exercise. We can talk about how to do it over the break if you guys haven't, in the exercise session if you haven't figured it out. Okay, so let's come back then. So now what have we decided? We have a kinematic space. When there's an ordering, it needs an ordering somehow. So we need an, if there's an ordering, then we have a kinematic space that's nicely given. I can draw this picture if I like. Now I'm trying to not make it an convex. I made it. It's almost as bad as before. Sorry about that. Okay, so E1, E2. But my variables are the xij, are the distance squared in here, and I can think about them as distances in the chords of this polygon. This is my kinematic space. And now in this space, we're going to find some question to ask whose answer is going to be related to scattering amplitudes. Okay, we'll talk about that in a little bit. Let me tell you something about this ordering. So this discussion was all very, very simple and general, but what theory are we talking about? The theory that we're talking about is theory of scalars. And it's going to be a theory of n by n matrices. So we're going to have scalars phi that are colored. So this is a colored particles. In particle physics, we have, in the strong interactions, we have quarks and gluons. And the quarks and gluons are associated with three colors. The quarks have one of three colors, red, green, or blue. There's an SU3 group that rotates them. The gluons have a color and an anti-color. Okay, that can be red, green bar, and so on. And so they're associated with 3 by 3 matrices. So what we're doing is taking a kind of a toy model of the gluons, where we have scalars that are just n by n matrices. They're n by n matrices, but they have an interaction which is UN invariant, SUN invariant. Okay? So our Lagrangian is going to have an interaction, which is G, some coupling constant, I'm not going to keep writing down again and again, trace of phi cubed. But trace phi cubed means if I write in indices phi ij, phi jk, phi ki, so the j's are summed, the k's are summed, the i's are summed. And so if I denote phi ij in an obvious graphical way. So if I write phi ij like this, as two arrows, where an arrow going this way means that the index is, let's say, downstairs, and there's another, so for example, I would have 1, 2, this is the index, 1 is down, the index 2 is up. So the arrows are just indicating whether in the matrix I have the upstairs arrow, I have the upstairs index or the downstairs index. Well, that interaction then looks like what? It looks like I is shared like this, K is shared like that, like so. Okay, so this would be index, let's say K, the way I wrote it. Maybe that will be whatever, index J, index K, and index I. Is that clear? Okay, And what you're supposed to do is just if you're calculating Feynman diagrams, even if you don't know what they are in detail, you're just supposed to draw pictures where you glue these things together, right? But exactly because they've given us what looks like this little small triangle here, little two-dimensional surface, little triangle here, the pictures are all naturally planar. Once you decide how the color lines are supposed to go, right? So there's going to be some part of this amplitude where it looks like color 1 goes, and then color 2, and then color 3, color 4, right? Once I decide what the colors are, that gives me an ordering with which to draw all of the diagrams. Okay, so for example, I can have a diagram that looks like this, where this would be color 1. So color 1 goes over here, and this would be color 2, whatever it is, color 3, color 4. And I'm emphasizing this small point that it's the colors, the choice of colors and how they flow that determines what the picture looks like. But it naturally gives an ordering for the external particles, right? So this is a diagram that I could draw. For the same color lines, this is another diagram that I could draw, right? But a diagram which looks like this, which you would sort of draw in a normal oops, sorry. Anyway, a diagram where they cross does not correspond to this ordering. Okay, so that's where the ordering comes from. When you have colored particles, then the external then the pattern in which the colors flow determine an ordering for the external particle. So that's the basic theory we're talking about. That's a connection. That's a connection to a color. Okay, so let's continue to look at this. Okay, so I'm going to call this momentum 1, momentum 2, momentum 3, and momentum 4. And again, this color line I'm going to call color 1. So I'll just put a 1 here, and a 2 here, a 3 here, and a 4 here. That 1 just tells me this is color 1, this is color 2, color 3, and color 4. Okay? You see already the connection with our picture, right? So I can draw my square here. I think about this momentum P1, P2, P3, and P4. Then if I draw this diagram, sorry, if I draw that line here, so sorry, let's look at this diagram first. So what is the momentum on the inside here? The momentum on the inside is P1 plus P2. See, P1 plus P2 is also what's associated with this region that's bounded, but with this line that's bounded by the regions 1 and 3. And that's exactly what we got from our momentum polygons, right? So if I draw my momentum polygon, this is x13, and x13 is exactly equal to P1 plus P2 squared. In this Feynman diagram, I'm supposed to have a propagator, which is 1 over P1 plus P2 squared. Okay, but you see that there's a correspondence between this diagram and this triangulation of the square. And of course, the exact correspondence is a very natural one. Just draw the dual to this triangulation. Put a point in the center of every triangle. Okay. And so that cubic diagram is the dual of this triangulation and precisely corresponds, if you fatten it out, if you thicken the lines, it precisely corresponds to this diagram. Another way of seeing the connection between, well, I'll leave it at that. Okay, so now we see something extra nice about these x's. These x's are directly the objects that show up in the Feynman diagrams. They're exactly the objects that show up in the propagators of the Feynman diagrams. Let's do a slightly bigger example. Okay, so this momentum is P1, this propagator would be 1 over P1 plus P2 squared. This one would be 1 over P1 plus P2 plus P3 squared. Okay, by the way, there's a very small annoyance if you do these things in terms of the momenta, because who says that's P1 plus P2? It could also be negative P3, negative P4, negative P5. Okay, so this is equivalently 1 over P3 plus P4 plus P5 squared, and so on. This is 1 over P4 plus P5 squared. But if I draw the picture of the momentum polygon in this case, so I have 1, 2, 3, 4, 5. Well, let's just see. Here I see 1, 3. So this would be region 1, region 2, region 3, region 4, region 5. So I see a 1, 3 and a 1, 4. So I put a 1, 3 and a 1, 4 here. And indeed, if I look at the dual of this diagram, it looks exactly like that one. Okay. But again, the chords in this triangulation, so here I see the chord x13 and x14. And nicely, I see that x13 is exactly P1 plus P2 squared. X14 is exactly P1 plus P2 plus P3 squared. And again, the whole point is, since it's this distance squared, I don't need to tell you if it's this plus that or that plus that plus that. So this sort of annoyance in how I label it even is gone. I just give x13. Okay, and that just is equal to, it's automatically equal to the other side. So that's the sense in which we trivialize momentum conservation. Okay. So I'll just take stock again for a second. We've just talked about now a theory of colored scalars. Our canvas is, we started off with momenta, but we decided to draw this momentum polygon, which is natural because we have in color ordering for the particles. And the kinematic space is then just labeled by the x's, right? The x's give me an independent basis of all possible dot products. On top of that, the x's are directly the variables that show up in the amplitude. Okay. And what is the amplitude? So let's finally write down a formula for the amplitude. See, so now we have defined our canvas, and let's just even take a peek at the answer. So our canvas is just the space of xij's as totally independent variables. Okay? But we want to think of these as associated with chords of an n-gon. By the way, now this n-gon is just a completely abstract n-gon. I mean, I can, when I draw it now, I can draw it any way I like. Because I'm just, I don't have to give a picture of the momenta anymore. These x's are just the basis for all the invariants. So I just give an x associated with every chord of the n-gon. So I just draw an abstract n-gon now. The way I draw it doesn't even matter. But with every chord of this n-gon, I have a variable xij. And what is the amplitude? The amplitude is a sum over all the triangulations. So every Feynman diagram is some triangulation of this n-gon. Every Feynman diagram is some triangulation of this n-gon. So for every triangulation P, I take the product of 1 over the xij's for the ij's that are inside that triangulation. This is the answer, sort of cheating from quantum field theory, right? That's what we know the answer is supposed to be. All right? And so we have now defined our problem. Okay, so let's say we didn't know anything about this. Say we didn't know anything about this. What kind of question could we ask in the space of diagonals of a polygon, where I've attached a variable x to every diagonal? What kind of question in this space gives me this answer? Right? So I hope you see it starts getting a much more concrete question. Now, before telling you about what the question, and of course, the answer ends up being that the amplitude is the canonical form of an isosahedron that lives in kinematic space. Okay, so that's what the answer is going to end up being. So Simone is going to tell you something about canonical forms and positive geometries and so on. So I'll say maybe a little bit about it. But just to sort of jump ahead, in this X space, directly in this X space, we're going to find an isosahedron. And there's a question to ask of the isosahedron. The canonical form of that isosahedron is going to give us this as an answer. Okay, so that's the nature of the kind of thing that we're going to be looking for. Yes.
Just a bit more what you mean by triangulation.
Oh yes, sorry, right. So I literally mean. So what is a triangulation? Triangulation. Let's go to higher points. A triangulation is any sort of maximal collection of x's of chords that you can draw that don't cross each other. Okay, so any such maximal collection has n minus 3 chords in it. Okay, so here's a triangulation. Okay, so it just breaks up the polygon into triangles, but the vertices of the triangles have to be the external guys. If there's no, so this is not a triangulation. Well, this point in the middle is not there. Okay, so when I mean triangulation, I mean just something which is chosen, whose vertices are chosen from the outside. Okay. Right. So this is a triangulation. So at 6 points, this and its cyclic friends are a triangulation. This is a triangulation, my favorite triangulation. Okay. This is a triangulation. And these are the classes of triangulations we have, right? Yes.
So like you started with like n scalars and the answer just depends on n minus 3 chords. Is there any physical?
The answer is not n minus 3 chords, n minus 3 over 2.
Right.
Okay, it's n2 su minus n. And those n2 su minus n are exactly all the distance squares, all the sums of the momenta from I to j minus 1. And that is the basis for all possible dot products. Okay, so any answer has to be expressible in terms of these x's. I even gave you that formula that gives you the map between the x's and dot products. Okay, so anything you can write in terms of the x's. But what's lovely is that the amplitude is this very simple. See, if you wrote this in terms of dot products, it would be complicated. But when I write them in terms of x's, it's simple. So the x's are this a simple geometric interpretation, and we also have a simple, and they allow us to write the amplitude in a simple way. But let me say a final thing about this, and then we'll take a break. And just so you know where we're going, I will then I will first talk about what the analogous questions are in cosmology, because I want you to see how extremely basic and simple all of this stuff is. All that's going to happen is our kinematic space is going to get a little bit bigger, okay? But it's going to be very similar objects. This story is all going to be about triangulations and chords that don't cross each other. When we talk about cosmology, on top of it, we have to sort of have a picture of a sort of a Russian doll that I can make from these chords. So these chords also define subpolygons, and I have to have pictures of non-overlapping subpolygons, right? So it's a one step up in the combinatorics. But once we make that basic realization, the kinds of connection that we make between geometry and particle physics by the isosahedron is going to generalize to cosmology. But I'm going in this way to emphasize how super basic the issues are. It's all about thinking about the kinematic space slowly and correctly. Yes, sorry.
Does this amplitude depend on the initial ordering that we vote?
Very much so, absolutely. So this is an amplitude for the color ordering 1, 2 up to n. Okay, so exactly. I've decided that I've decided how it's color 1, color 2, color 3, color 4, or if you like, I use this to define what I mean by 1, 2, 3 up to n. There will be an amplitude for other orderings, and for the other orderings, you would have to draw their own polygon where you reorder the x's. It's an interesting question to learn how to write the x's for a second ordering in terms of the x's for the first one, which you certainly can because you can write all the dot products in terms of the x's. So there's a simple formula that takes you back and forth between different orderings. But this formula is for a fixed order. So thank you very much. Yes.
How does this picture change if I have more than one type of field in my Lagrange?
Excellent question. Yeah, if you have more than one kind of field, well, let me let me answer a second question first, because it's slightly simple, but well, I'll come to your question in a second. Like here, our basic interaction was this one, right? And so this gives us triangulations of the n-gon. That's clear because every triangle, so another way of thinking about this, every triangle in this triangulation is one of those interactions, right? That was the sort of point here, right? Every triangle here is one of these interactions. Now, what if I have a trace phi cubed theory? What if I had a trace phi to the 4 theory? Or even a combination of trace phi cubed and trace phi to the 4? Well, if I trace phi to the 4, that means I also have this as a basic interaction. It's colored so they always look like this. They always have this sort of planarity about them. But what would I do there? Well, it would be a sum over triangulations and quadrangulations, right? And any combination of triangles and quadrangles. Okay, so for every kind of object, and if you have phi to the p interactions, you'd have a p angulation, but you could have p angles for all possible p, and then you just plunk them all down, and you write down the product of all the couplings that go along with it. Okay? In the case of the triangulation, I should have written down a g to the n minus 2 that counts all these coupling constants, but I just didn't write it down because it's uniform in front of everything. But in principle, I can sum over triangulations, quadrangulations, everything, if I have a more general theory. And now if I have more than one kind of particle, then I have to have different kinds of triangle. Okay, so I'd have, or for example, I could, so let's say I have, if I have like phi I, phi j, phi k, where these range over the number of particles that have an interaction like that, then I have to have a triangle that's sort of further labeled by I, j, and k. So I sum over triangulations, but on top of that, I decorate every edge of the triangle with an index. So any theory of scalars, any number of them, anything you want, any interactions, any arbitrary Lagrangian can be cast in this picture of sums over triangles, quadrangles, and so on, with appropriate decoration on the edges. Did that answer your question?
Yeah, I just had a small thought, like if I introduce spin into this is
Yes.
just for scalars.
Yes.
Is spin just in another variable?
Spin, in this language, spin could be another variable. So you could even proceed in this way. And that's perfectly okay. What appears to be the case is that in this way of thinking about things, as is true in textbook quantum field theory, spin looks like a pain in the ass. When you add spin, everything looks more complicated. Lagrange looks more complicated. Interactions are more complicated. Yang-Mills theory looks much more complicated than phi to the 4th theory, which in turn looks much less complicated than GR, right? When you do things in typical field theory. And thinking about it in this way would not change that, right? Just another index, another something more painful. The actual fact is that the actual scattering amplitudes go the other way around. As the spin goes higher, they become simpler. So it's very mysterious from the traditional textbook perspective. You would not expect it at all. But in a very precise sense, scalar theories are much more complicated than Yang-Mills theory. That's much more complicated than gravity. Okay? So this way of thinking about spin does not seem to be the right way to go. Although you could certainly try to do it and proceed. I just had one more comment and then we have to end. Is that okay? Sorry. So just one comment quickly. Sorry. So this formula has in it two sort of crucial features. Okay? This formula makes it clear that the answer is compatible with the local interactions in space-time and is compatible with unitarity in quantity. And this is a special case of a more general fact, but we can see it already here in this very simple example, that the purpose in life of the diagrams, I told you, is to make these two things obvious. But there's a beautiful fact that if someone just hands you the answer and says, trust me, I summed all the diagrams, okay? You can check if they're right or wrong without summing all the diagrams yourself. Okay? This is a remarkable and beautiful fact that locality and unitarity are imprinted in a very sharp way on what the amplitudes look like in the end, okay? So this fact gives us a big target when we're trying to see some other principles that these objects can come from. Because we want to see where these sort of simple facts, what other world of ideas might give rise to these very basic facts. So what is this basic fact? Locality tells us, well, here it's totally obvious, that the only singularities that this thing has are just poles in X, okay? Poles in X, remember, look like 1 over the sum of a bunch of momenta squared. So what could it have been? Well, if it's a totally random general rational function, I could have had poles like p squared, q squared, minus r squared, t squared. Okay, that's a kind of crazy pole that I could have. Maybe this translates to some xx minus xx, some junk like that. Okay, so I don't have poles like that. My only poles are in 1 over x. So 1 over p squared is exactly, the Green's function for the D'Alembert. Okay, so that's locality in space-time. It says the only way the amplitude can blow up is when there's a particle that's propagating between two points over a long distance, okay? Not in a more complicated way, right? So that's locality. Locality is that we just have poles, simple poles, in x size. And unitarity shows up in a beautiful way right in the neighborhood of locality. Let's say I have a process like this. If the momenta here are generic, then we said this guy is virtual, right? There's a 1 over p1 plus p2 squared, and this is not equal to 0 in general. But let's say you tune p1 plus p2 so that this does go to 0. But that does go to 0. There's a pole in the answer. The answer is blowing up. It's a resonance. Well, what do you know about resonances? That means this particle that we thought was virtual has actually become real. But then we know exactly what the amplitude has to look like. This is a consequence of unitarity. In the neighborhood where that goes to 0, I have to be able to pull out this 1 over p1 plus p2 squared. That's the pole that's going to 0. But then what I have to have is the amplitude for this process on the left times this process on the right. 1, 2, intermediate, 3, 4. Okay, so it has to factorize. In the neighborhood of the pole, the amplitude has to factorize. Now, what does that look like in this language? So, I want to think that the amplitude is a function. The amplitude is a function of the x's of this n-bar. But what happens as this x, let's say, this x star goes to 0? Well, unitarity tells me that the amplitude has to go like 1 over x star, but what it multiplies is the amplitude for this left n-gon times the amplitude A left times the amplitude for the right. Okay. So factorization looks like exactly what you would think it looks like in the polygon language. Something else that's very natural in the polygon. Okay. When this chord goes to 0, the amplitude has to factorize into the product of something on the left and something on the right. Okay, so now the sum over all triangulations clearly does that. And why? Because, for example, if I'm summing over all triangulations, if I'm looking for the part of the amplitude that has a pole as x star goes to 0, I have to look at those triangulations that contain this chord. Otherwise, it's not going to be blowing up. But as soon as it contains this chord, the rest of the things I have there cannot have a chord that crosses this, because it wouldn't be a triangulation anymore. So any triangulation that contains this chord must just look like something that triangulates the left and something that triangulates the right. Okay, and I'm summing over all the possible triangulations, therefore I get this factorization, right? Okay, so you see that the story of these amplitudes in X space, the story of these A-colored amplitudes in X space is all about non-overlapping chords. I have to take all the possible non-overlapping chords. Every single one has the 1 over x associated with them. The amplitude is the sum of the product of all these 1 over x's. But taking care of non-overlapping chords means that I have objects that satisfy both locality in space-time as well as quantum mechanical unitarity. So when we come back, and I'm sorry for going over, we're going to switch gears and talk about what happens, what the observable is when we talk about cosmology and how it enriches the story from non-overlapping chords to non-overlapping subpolygons. And having gotten into the kinematic space and into the spirit of things, we will then talk about what the combinatorial geometric objects are that captures all of these properties. All right, thank you.